Okay, welcome everybody. I'd like to introduce today's speaker, Professor Avshalom Elitzur from Chapman University and IAR, the Israel Institute for Advanced Research. Avshalom Elitzur earned his PhD from Tel Aviv University under the guidance of Yakir Aronov. He has held appointments as a lecturer and visiting professor in several universities, among them Bar Ilan University and the Université Joseph Fourier in Grenoble, France. He is currently a visiting professor at the Institute for Quantum Studies at Chapman University in California. He is the co-author of the Elitzur-Weidman experiment and the founder of VR. His broad research, and you can see this on his website, it spans over quantum mechanics, relativity theory, living systems thermodynamics, and many other interesting ideas. I'm going to mention on a personal note, I would like to acknowledge Avshalom is one of my first mentors in this field. Over 20 years ago, after I read Avshalom's popular book called Zman V'Toda'ah, Time and Consciousness, I met with Avshalom, who advised me, encouraged me, and now I'm privileged to introduce him. So let's welcome Professor Elitzur, who will speak about life overnight. Extraterrestrial biospheres may evolve much faster. Avshalom.
Thank you, Nathaniel. Yeah, this is the time in which we recall our great masters, Noam Lahav and Shneur Lifson, Zichronam Livracha. And it's time to rejoice the joining of young new scientists to this Origins of Life group, which is now, I believe, more than 40 years old. And thank you all for this opportunity to meet together. So here is the question I'm going to ask. This is one of the cases in which the physicists can plead ignorance about all kinds of biological details when you come from the viewpoint of thermodynamics, which enables you to make some generalizations about all aspects, all kinds of life without necessarily knowing them. So, yeah. So here's what, rather let's go into the questions. We are thinking about, so here we have two great questions. First, how did life emerge on Earth? And then are we alone in the universe? And they are related. So let me just recall how I see the emergence of life. I guess, and this is what the models today tell us. We had a world with inanimate matter, so there were all kinds of random processes without anything having any function or anything which we know from life. But then something happened in which a certain process, was it a single molecule, was it a group of molecules, was it, but some entity did something on the environment which resulted in creating just another identical or very similar system to that one. So this is autocatalysis. And once this has happened, then we expect, and of course, if there has been enough substrates for such a thing to emerge, if substrates abounded to allow for this autocatalysis, then something amazing happens. A very random, microscopic, unnoticed event magnifies, amplifies into something huge, almost irreversible, and takes over whatever lake or pond or ocean in which it has occurred, once again, assuming that substrates abounded for that. Now you have to ask for another thing, that this autocatalysis would not be precise, such that variations would occur, but they themselves would be somewhat stable. Here is where you're asking a lot. But should that happen, then evolution takes over at that moment. Now there is natural selection, and now you go somewhere, eat your lunch, come back, and you see that this process has advanced. So this is evolution, and this is the emergence of life, which inevitably has to diversify once you are spreading over a population, and then you begin producing all kinds of species. So then the adaptation now is not of life to the inanimate world, but a higher process in which life has to adapt to life itself, to compete with life itself with another form of life. So this is another beautiful thing. Ecology then takes over, and we have a biosphere with all this intricate web of interrelations and between the organisms. And this is a toy model of mine. I had opportunities to present it here in Ilosol. These are all information processing processes. I mean, evolution is information processing. There is memory, there is learning. You can show that there is some kind of intelligence. And then this intelligence, which is implicit at the level of the population or the species, sometimes you can see that a colony of ants is much wiser than the ant itself. So there is an emergence later that emerges as an individual property of the organism, and then you see intelligence. And here again, once there are many intelligent guys around, then they have to be compete or to they have to cooperate with one another. And then you see the next step in which is civilization, which is what we have here. So this is the story that we had here on Earth, and now we are looking at the night. For me, living in a moshav, so I can still see stars, which you people in the city probably do not. And then you ask yourself every night when you go to take a walk, are we alone in the universe? And what's the chance of somebody thinking the same thoughts in one of those near one of those shining stars? And then I have to ask the following question. So evolution, and here I'm coming from the viewpoint of thermodynamics, which I'll explain in a minute. Evolution is a function of probabilities. In order for the occurrence of something, so at the beginning you have something random, and then you need the feeding of randomness into the genome, into evolution, and then these probabilities require, what do they require? Trivial matter, trivial energy, space, and time. And I want to ask something about time. So biologists tell us that life has emerged on this planet something somewhat more than 4 billion years, which is nice, but is that fast? Is that slow? And what I want to propose is that we have been and we are extremely slow, and that evolution and the emergence of life can take much faster. I wanted to say that I resisted the temptation of making my model quantitative. Why should I lie? I succumbed to the temptation of not making it quantitative, going into the details, equations of physics, astronomy, astrophysics, and chemistry, and so on. Rather, I'll present it first at the qualitative level. Should that make sense, then later we can ask for astrophysics and chemistry and so on to feed their numbers. So this is what I'm going to do. And here's my argument. Increase one of the first two of them, all three together. I think that the fourth can be reduced by orders of magnitude. And nothing, so I don't think that I'm saying something really radical. So let me just say something about thermodynamics. Recently, I had the privilege of assisting with two guys from Weizmann Institute, translated Schrödinger's famous book, What is Life? And being the scientific editor, I abused my position in order to write an introduction, an epilogue to this book, and have Schrödinger been alive, he would not be pleased, because he would say, this is a small book, and why did you write such an epilogue, which is almost as long as the book? But Schrödinger did two things in that book. One, which is both of them are admirable. But in one of them, he went into the details. He was a very good physicist and a very good biologist of his time. So he really took the trouble of going into the molecular and physical mathematical details of that molecule, which he assumed to be, which would later turn out to be DNA. So this is one part of his work, which is, of course, admirable, even with all the errors that he inevitably committed. But the other thing is that he tried to give a kind of broad view about what life is. And this is where he proposed the importance of entropy to the understanding of life. So,
Avshalom, you should be seen better on the screen.
I should
We
see.
only see your nose. That's much better. You look so
I'm not.
beautiful.
It's Schrödinger, which is important.
No,
Yes,
go
thank you,
up,
Dora.
go up.
Okay, so we need some entropy. Now, what does entropy mean? Larger probabilities. So what I'm saying is that while the two values which of the resources that I mentioned are subject to conservation laws, which is matter and energy, one is not conserved. Entropy always increases within a closed system, even in an open system, about which I'll comment in a moment. But then this entropy, which looks like the antithesis of life, of the emergence of biological complexity, is the very progenitor of complexity. So in order to have life, you need information just to transmit the adaptation from one generation to the other. And then in order to be a machine which works efficiently, then you have to be sufficiently complex, and both information and complexity from the mathematical point of view, their definitions and their measures are dependent on those of entropy. So you need the capability or the potential for entropy to be great in such an environment in order to have information and complexity, which are the hallmarks of life. So let me just explain, just to give an illustration. Here you see a small niche which is self-sufficient. That is all the matter and energy, all the matter there is always recycled, but not the energy. Okay, so even if you make a very large system like that, and put a lot of energy there, which doesn't kill the organisms there. It is large enough for them. And they have all the energy they need, they'll soon die out because it is not energy that they need. And this was Schrödinger's genius. It is the kind of energy, low entropy energy, which they need, which later will increase. So you have to bring again light, not because they lack energy. They have all the energy they need, but they need the kind of order source in order to combat the entropy increase, which is not conserved there. I think that Roger Penrose gave the best illustration of that. If you just count the number of photons coming from the sun to Earth and then leaving us to outer space. So you see fewer blue photons coming from the sun, a greater number of red photons leaving us to outer space, which means that they did work here, and the light would be of no use, infrared light, if it stays here. On the contrary, so we always need concentrated, low entropy energy coming in order to be released to outer space in higher entropy, such that this is what we managed to do for 4 billion years to preserve the entropy on Earth and not going up too much until these days. And let me mention another toy model of mine, which I developed with Professor Eli Cohen from Bar-Ilan University, the ski lift pathway, in which I gave a talk in Chapman University a few months ago, so you can find a detailed talk this time with the figures in Chapman's website. So many of you probably know the idea that in order to create complexity, biological complexity, you do something which looks wasteful. You first of all create surplus order, and then you spoil it downwards. So I should say, in order to avoid confusion, I should say that if you take the scale of high order and low order, then information and complexity are somewhere in between. If something is complex, that means that it is not disordered, because that is no complexity, but that means that it is not too ordered, because that wouldn't be complexity either. So if you take an organism and make it and let it perish and disintegrate, then ashes to ashes, dust to dust, entropy goes up and there is no life. But if you make that organism much more ordered, too ordered, then you would kill it again. So the complexity is somewhere in between, and this is why we use this analogy of the ski lift. If you are somewhere on this mountain, so you liken the tip of the mountain to high order and the base to low order, and it goes also with the mathematical idea that there on the tip there are few microstates, many more microstates down there, and also the analogy of gravity helps you here, because it takes energy to go from low order to high order. It's spontaneous to decay to low order. Now the question is, which for us was a great surprise, what happens when you have a complex state and you want to go to another complex state? So here it is. It is not the direct path, but what looks like something which is very wasteful. You first increase the order much more than the amount of order than you need, and then you glide back, spoiling it again towards the desired complex state. I gave last time, I think it was 2 or 3 years ago, in Hebrew University, I gave a detailed mathematical proof that this is the most efficient one. And this is what we are going to need, because Schrödinger said that the sun is a source of, and people ridiculed him for that, not Penrose, of course. So he said that the sun is not only the source of energy, but it is the source of negative entropy. The energy coming from the sun is so ordered that it feeds us with negative entropy, and this is how we combat our entropy. Our model says that this is correct, but that we ourselves are creating such sources of negative entropy within ourselves, within our environments, in order to increase our complexity. I may need that later. And now, this is an analogy, but I think that it helps us think. We perceive time in different organisms perceive time in different ways. Actually, I don't know whether you can see it, but at this very moment, there is a fly which is harassing me. With some luck, you may see it. So for this fly, if I try to smash it, then of course it will laugh at me if I don't do it very efficiently, because he or she perceives time differently than the way that I perceive them. What I consider to be a very fast blow, for them it just like a leaf falling slowly from a well, not always, if you remember Obama and the fly. But here it is. The fly perceives time differently, and when we have to combat microorganisms, they beat us always, and unfortunately, they'll keep beating us because their evolution is much, much faster. And the question is, why is their evolution much faster? It's an interesting question. Why, for some organisms, their nervous system works so much more efficiently than ours, then they can evade our attempts to squash them. But why is it that microorganisms beat us evolutionarily, such that they, whether they are pests in our fields or whether they are parasites in our body, why is it that their evolution is so fast? Is it because they are very small? Yes. But what prevents such a fast evolution to occur at multicellular, large macroscopic organisms? You need much more space, you need much more matter, and you need much more energy, which on this planet, we don't have enough. So this is why I'm asking this question. So let just give you some examples from extant life. We see that the biodiversity is much greater in near the equator in tropical zones. What would happen in a planet which is all tropical? Let me just use the example of the oceans. You can see that in the oceans too, the temperature is very important, but then also you need to have water. So it is the diversity of the oceans is much greater, where light can actually enter the water into the abyss. So the presence of these two elements, water or some other liquid, some other hydrosphere, and energy, this is what is so important for the emergence of life. So we have such an amazing diversity at the tropical zone. Not too hard to conceive a planet which is all tropical and which is even hotter, warmer, hotter, or whatever. We have 7/10 of our surface having water. What if it was larger? So think about, first of all, the importance of abundance of energy, to the extent there must be an upper bound such that it will not destroy life. Think about the rapid speciation following mass extinctions. This is something known for paleontologists and evolutionary biologists, that after every calamity, you have a greater diversification and you have many, many more species. So what could that be? Can you think about a planet which has all a tropical climate or even much warmer and which has endured much more frequent extinctions? Now, here's another question. When we think about the origins of life, so as I said, people are talking about something more than 4 billion years ago. But it turns out that although the planet Earth has been extremely inhospitable before the emergence of life, it was considered to be very inhospitable, and then it became cooler. It was very warm, being bombarded by comets and so on and so on. So it was hellish and hot, but then it cooled. And then the interesting thing is that life emerged within what, 500 million years or even less. And people call it the problem of the window of time. How come that life emerged so fast? I mean, if that is the case, then life's emergence is bound to occur. And here I'm drawing on person, I think, oh, I'm so sorry that I didn't write down his name. Carl Voss, probably known to many of you. I consider to be one of the most daring and interesting biologists of our time, and he was studying the extremophiles, thermophiles, and he was the man who revolutionized the whole taxonomy of life, arguing that archaea is a completely different kingdom. But something that he said struck me some 20 years ago when he said it, and I find it really amazing. So what are these extremophiles, say, these thermophile microorganisms that you find today only in hot vents deep in the ocean? So we think that these are organisms which would, if you put them in your coffee, they would die of being too cold because they need a much larger temperature. So we think that, that's nice. Look how nicely they have adapted to very hot environment. And what Carl Voss said is, no, this is not the case. It is we miserable creatures who have managed to adapt to such cold environments. So the Earth has cooled, and when Earth was hot, these are the archaea that dominated our Earth. So my question is this: could you conceive of a planet that did not cool down, that remained very hot? Would it be too much to expect that even the evolution of multicellular organisms would be intense, would be fast? Because I guess that at that time, at that area, it has been fast in order to bring this resistance, amazing resistance to such heat that would make us completely denaturate. Yeah, so what if Earth has never cooled down? And what if we have endured many more catastrophes on evolution, which made us diversify even more. If it were too much, then we wouldn't progress. If it were too little, we wouldn't progress. But even this fine tuning is very likely not the most favorable one that we have here on Earth. So this is the question of hydrothermal vents and the origins of life. I am thinking, so what I'm thinking is that every time that we look up there at the sky, it is always known that we are very anthropomorphic, and we remain anthropomorphic, although we try to release ourselves from the preconceptions of life as we know them here on Earth. But again, thermodynamics tells you the following, that the laws of thermodynamics are ubiquitous. That is, they are independent of the chemical composition of the system and the type of energy which is being processed in them. So here you can make some bets. You can say, if I see an alien, I have no idea how it looks like. I can make guesses about its symmetry and so on. But if I want to shoot that guy, I know where I should aim. I mean, show me where this guy produces the greatest heat, and this is where the biological processes are the most intense. Life means being a machine. Machine is doing work. Every time that you convert one kind of energy into work, some heat must be released. This is ubiquitous. It doesn't matter what kind of technology you're using. So this is why I'm asking, every time that we look at life, we try to tell ourselves, don't always think about carbon, don't think about this. And still, I believe that we are too much bound to terrestrial life when we are asking ourselves where to look like. I suggest look for much more exotic places. So, and this is not going to be a long talk. So I'm going to discuss, and then I'll leave a lot of room for your questions. So I'm thinking about the four resources that we have. You want to create life? Give me matter, give me energy, give me space, give me time. Okay, you have it. So just think about a much massive plant, which greater volume, which greater surface, and then there's such a volume, gravity will help you that even if it's very hot, then the water, whatever liquid is there, will not evaporate, that the atmosphere will be bound to it and it will not leave it. So that is given to you if you have a much larger planet. Given sufficient energy, chemical richness will follow because you have much more matter there. So the kind of compositions even before life, this kind of increasing complexity of the molecules and the chemicals there must be much greater than ours, such that when that autocatalytic system emerges, then many more substrates abound for it. And for some, now here a student, I believe it was a student of Doron or no, of Gonen, who said, wait, why are you saying that? Sometimes you need compartmentalization. I mean, sometimes you don't need too great volume. You need these guys to come together in order to do something. Okay, so I'm qualifying it. You need much larger volume, but with the kind of surface that will enable every once in a while some guys, some chemicals, molecules, or whatever to come together to be compartmentalized, and then later emerge once they did that, and then later go to the vast area. And of course, there is an upper bound for gravity. Don't be too heavy such that it will destroy all life and will suffocate you and will not. But this one, and once again, I don't bring figures, but the physics here is quite simple. Increase the G for, I don't know, 10 times, that is not going to be a great biological hurdle. But that means that you have much greater amount of matter, and of course, later space will be. But now it is energy which is problematic. So you need solar or thermal energy, which here on Earth we have very little. So it is energy which enables you to activate several chemical reactions that you want to have. You need it to do work. And once you have fluids, it is heat. It is the energy of heat which brings together, which makes all the turbulences in order to give you that soup and in order to mix the chemicals you want into the chemicals, the complex chemicals, amino acids, whatever that you need. So this is energy. And of course, it also has an upper bound. Don't burn them, don't melt them, don't bring them to the point of denaturation such that you will destroy all structures. Think about the thermal vents. They managed to do that. But now thermal vents are very, very small and they're confined to very small places on Earth. But the upper bound on energy, which is here, it is considerably more serious than that of gravity, but it's not that great. And now space. Once you have a larger hydrosphere, larger atmosphere, then you have much more room for display, for the varieties, for all the combinations. And here combinatorics come into place. You have more molecules, greater amounts of matter to do that, more energy, and they all give you a greater likelihood for varieties. And once again, I think that we all agree that the emergence of life is this miraculous transition from a very rare, unnoticeable, ridiculously small, random, microscopic event, which happened to be autocatalytic. Something has emerged from some substrates. That something is doing some work, whether it's an enzyme or whatever, or a group, or those of Dawn and so on, which everybody catalyzes everybody. And they're doing things which I'll never understand, but it suffices to say that at the end of this amazingly complex work, another similar system appears. Once that happens, then within that lake or that ocean, within, I don't know, hours, something has changed, and from now on, it gallops further. Given the possibility, which I don't know still how to do that you don't want the replication to be too precise in order to have variations, but you don't want it to be too imprecise in order for the variations to be washed out. And this is, I guess, what most people of the origins of life are trying to do now. And with this, I come to a close. I say that you have four resources, the four basic elements of physical reality: matter, energy, space, and time. Increase one of them, two, three of them, which you're not asking too much when you are looking at this amazingly huge, awesome universe. And once you can have them, I believe that time can be reduced by orders of magnitude. So life can emerge overnight compared to ours. So these are the basic thermodynamic considerations, which once again, I didn't make them quantitative because first of all, just I want to present the idea in itself in a qualitative way to see if it makes sense. Then you can feed the equations with the figures, the G, the gravity, the Celsius, and so on. So with much respect to our great and beloved patriarch, warm little pond? Forget it. Give me a huge, sizzling, boiling ocean. This is what you need in order for life to emerge. And if you can leave it for that time. I think about gradation scenarios. So if you want it to be gradual, in order not to destroy life, this is something that with my very limited astronomical imagination, I can think about. Think about a very aqueous planet where just a certain region of it, say half of it, the part which is exposed to its sun, to the star and so on, is very hot. So if life emerges at the fringes of it, then gradually it can go into it if it's vast enough, if you have enough energy, enough volume, space, and enough material to do that, then you're going to use that available energy. And I believe that life would become extremophile, thermophile, to the extent that I believe will make them much faster. I think about catastrophes like a sun turning into a red giant, which we always afraid that it will, whether it's going to occur in the lifetime of our civilization before it destroys itself. But it could be for that billion years in which a star turns into a red giant. If there is a distant enough planet that can gradually accommodate to that, then they can flourish during that time, perhaps then being destroyed or perhaps learning to overcome it. But this is something which is also possible. And even the greenhouse warming, the calamity which we are bringing on ourselves and on our children with our amazing stupidity, when such a thing happens, and that civilization that gives rise to it will have to pay for it. But if it occurs just by itself for other reasons, what we consider to be a disaster can be just that. If a certain planet becomes a place which captures the energy of the sun for larger time, eventually, as Penrose says, it will radiate as the lower, higher entropy into the sun. But that can support life much better once they adapt to it. So that could be favorable. So this is what I'm thinking. Give me somewhere a very large planet with a lot, much more energy, much greater volume, great temperature and so on, more chemicals. And then overnight, just like the fly that I'm trying to squash or the bacteria in our test tube, which evolved just in front of our eyes, this is something that can happen to an entire biosphere and perhaps a civilization. So the gradation scenarios, as I said, is either an aqueous plant. Yeah, so I'm just repeating myself. From here, if I sometimes we can only go wilder and wilder. So where are they? So it looks like that if there is life on the universe, we are almost the dull and miserable and pathetic low life that we can think about. Just understanding that the time that the fourth ingredient, the fourth resource needed for life doesn't have to be so long, then we may be one of the lowest, least evolved kinds of life on Earth, on the universe. And then the question is, where are they and why aren't they coming? So one possibility is, and now I'm talking about as a theoretical physicist, I mean, if there is another civilization, we shouldn't think about them in terms of our physics, being having reached what we know today in quantum mechanics and general relativity and cosmology. We know so tiny little that just then, 100 years later, if we still survive, our physics will be completely different, and our possibilities of being in this universe so different. Then I doubt whether they would try to advance in the limited ways that we are thinking. There is a reason why I should be somewhat careful when mentioning Seth Lloyd, but he's a great scientist and a very imaginative one. So he even once proposed that every time that we see something which is anomalous in terms of astrophysics or cosmology, I'm thinking about questions like dark matter or galaxies which seem to be older than the universe and so on, which we, with our current cosmological and physical models, we think that they are strange. Are they strange, or are there also kinds of very advanced life which just manage to change not only their small planets, but entire galaxies or regions of the universe? I know that it is very wild, but it is worth mentioning. And from here, we can further go to speculate. Oh, what is he doing here? No, what I wanted to say is that no matter what we think how life emerged, life is very precious and important, and we should guide it. Thank you very much.
Thank you, Avshalom, for a very interesting and challenging talk. I suggest we have time for questions. Okay, I see some people already raising their hands. So you see on the bottom, there's
Oh, you are the moderator, Nathaniel. So please,
yes.
you take on. Oh, Andre, Doan. So yes, sure, many.
You can Avshalom, you can take the questions. You see
No,
the
please,
hands
you do.
raised?
Nathaniel, you are the gabbai.
Okay.
You count the people, and you are now the
Okay.
yeah.
But I suggest those who want to ask questions on the bottom, there's a little place where it says react. So if you press on react, you can raise your hand and I see some hands already raised. So I'm just gonna go I hope no one's insulted. I'm just going according to order that I see the hands. Amri Wandel. Amri,
Yeah,
we're
thank you,
being called.
Avshalom. Yeah, a very theoretical physics talk, a great talk, but as not so much theoretical, but more um, practical planetary scientist, I would say. I'm bothered by your statement that the bigger, the better. For example, the planet, or the hotter, the better. For one thing, I think at the beginning you said that Earth has very little energy. Actually, in terms, there is a term for this. It's called the habitable zone, the place where a planet can be reasonably a mild temperature to have liquid water. And the Earth is actually quite close to the inner edge of the solar system's habitable zone. It means that if Earth would be just according to many climate models, just 10% closer to the sun, it will already be more like Venus because there is a runaway scenario. So this is for the energy. Also, the um, vastness of the planet is not unlimited. I mean, if you have a bigger planet, then it will tend to be something like a gas giant or a sub-Neptune, which is not necessarily better fit to evolution of life as we know it. And I always repeat, as we know it, of course, a different life, maybe you're right, but our life kind of life, so not always bigger is better. And only finally, I want to point out something where you may have a point in planetary science. There is a model of planets that we don't know it in the solar system, but it's called the Haitian world, where you have a big ocean covered with hydrogen. And it may be like there are some planets that have been discovered. One of the most famous is 2K18b, and this is a sub-Neptune, and maybe it has a huge ocean under hydrogen cover. So I think we should not take everything you said is great, but we should take it with a grain of salt.
Very good. So I have a question here, Amri. Thank you very much. First of all, yeah, of course, if we are closer to the sun, then our atmosphere will evaporate, we will lose all the water. But what if gravity is larger? That is, that the planet is so large that the gene is much stronger, then it would counter that. And to the other question, yeah, of course, I know that the big planets are gaseous, but is there an astronomical law? And sorry for the ignorance, which says that there can't be rocky planets which are as big as say Jupiter and so on. I know that this is the case in our solar system, but is there something which prevents a large giving even a larger star, a larger sun? Is there something which prevents a rocky planet to exist, which is much larger? Does it has to be
Yeah,
gaseous?
it's exactly what you said. It's gravity. If it's bigger, it has more mass, it will retain more of its hydrogen and will become gas giant, which is outer layers are only hydrogen and helium, and it's difficult to see how life evolves in such a
Okay.
thing.
So then you say that nucleosynthesis under large amount, large masses so this is another limiting factor. I didn't know that. So this is something that I have to take into account. But you say that for a rocky planet, it couldn't be too large, that the laws of the formation of solar systems is such in general that
Yeah,
you
this is a well-established science. Models of planets depending on their mass. Beyond a certain mass, maybe something like the 10 or 50 times mass of Earth, you end up with a gas giant or
Fine,
supermassive.
fine. 10 times of that of Earth. Give me one.
No,
Okay.
not net radius, maybe, yeah. Mass, maybe 100 times the mass of Earth is the limit. So Neptune is, I think, Jupiter is 300 times Earth.
Can I
Neptune
comment?
is about 30.
So
Yeah,
I still can,
we're
I feel
getting too
comfortable
technical.
back
Can
again. Yeah,
yeah.
who is
Can I comment on that?
Alona?
Yeah, there is no planet formation theory these days that can explain a planet that is more than like 10, 15 Earth masses with no gas. Like no hydrogen, I mean. It's not like our secondary atmosphere. So it's really hard to explain very big planets, even if they close to their star, that composed mainly of refractories, rocks, and volatiles without hydrogen from the preliminary disk.
So we're still comfortable, I think.
Okay, next, Christian Mayer is raising his hand.
Okay, well, thank you very much for this very inspiring talk. I would just see another factor which would influence the velocity of evolution, which would be the sequence of generation. Like if an initial organism in evolution would live forever, would have an eternal lifetime, the evolution would stop. So I would see that there's an important factor is the individual lifetime every organism has. That's maybe one reason why the fly is undergoing a more rapid evolution, because it has a shorter lifetime and a more rapid proliferation. So what do you think about that? Just sequence of generation as a factor.
Very good. Yeah, I love it. I love to toy with. Here in my yard, I have a very big Sudanese turtle, which is that big, and paleontologists tell you that they have stayed the same for millions of years because they age a lot, and they don't. There are too little generations there. That's interesting what you say, because that limits, because that says that if you're a multicellular, then if you live longer, then evolution will be slower.
Slow down, yeah, right.
Slow down. It takes me, but I'm asking too much. It takes me to another model which I presented here in this Origins of Life, and I called it, but it's highly kind of speculative. I try to derive a generalized biogenetic law, like that of Haeckel and von Baer. And I say the following, but with this I'm very confident. All the properties that you find in individual organisms, which you think that they are very advanced, they exist earlier in the form of the population. The example which I love most is the tree. We have an evolutionary tree, so we draw it as a tree. But one of the products of this evolutionary tree is a tree in itself. So you can see that, think, for example, about metabolism. Viruses do not metabolize, but their population metabolizes, of course, because they die and recreate. You can see that some populations of multicellular organisms are capable of memory, of perception, or even more complicated, cognitive functions, which look even like kind of intelligence. So I have this model, which is again only qualitative and not much quantitative. So I think that in this case, so if you have an abundance of matter, I'm just following you. If you have an abundance of matter and abundance of energy and space, but then you don't have too many generations, still, I would say that this abundance would help the individual processes, which is also a kind of evolution. I mean, if you evolve during your long lifetime as an elephant, and then you undergo the natural selection, you bring to the next generation something which is better probably than the fly or the rabbit. It goes into biology, which is very subtle, and I don't pretend to understand perfectly. But I agree with you that this is a limiting factor to the kind of sweeping generalizations that I have made, and that I should take it into account.
Okay, thanks.
But isn't it true that more recent animals like primates are longer living, therefore slower evolving?
Mhm.
Yeah, but that's the question. Sure. So I think it was George Gaylord Simpson, Major Trends in Evolution. It's now 60 years old, the book, so I don't know how update it is. But it says that as you go, evolution favors larger animals, longer spans. I mean, the largest organism to have existed ever is the blue whale, more than the dinosaurs and so on. So the trend of evolution is to go into the individual. But that doesn't mean that the individual doesn't go evolution. First of all, it goes evolution within itself. There is learning, there is development. Um, so yes, and on the other hand, so we might be being anthropomorphic. You say that evolution brings organisms which have longer life, the primates and the mammals, but we may just being ridiculous. What about insects? They are not less advanced than us. Unless, I mean, they are, you understand what I'm saying? We think that we are at the top of evolution, but the ant or the mosquito are, they claim that they are equal to mine. They have different strategies. So still, the comment of Christian is important, and I think that what you, Aviv, are saying, yeah, I have to think about it. So I'm not sure that evolution favors longer lifespans. It is only we look at ourselves and we think that we are much more advanced, but it doesn't have to be the case. No, I think, and then, of course, now we are evolving not as individuals, but as societies, as civilizations. And once again, we need more space, more matter, more energy to the gloomy point that we have come here. So we are not escaping evolution. And have we had the larger planet, then also the evolution of the biosphere or even of civilization would be greater. Yeah. I mean, if you have a larger planet with all the resources that I'm mentioning, and it gives rise to a civilization, the advance of this civilization, I'm answering you, Aviv, the advance of this civilization, even though these are individual organisms that live longer, would again be speeded up.
Okay. See some hands. Vadivel has a hand raised. Yep.
Hello, Prof. Thank you for the lecture. It's very interesting for the theoretical point of view. I have a question, maybe because there could be another point. In addition, maybe it's the pressure. In such a case, maybe the driving force with the living group pressure, maybe that pressuring the whole reaction.
You're talking about pressure?
Yeah, I'm telling you, like not in the scientific way, practically the living groups, they're always pressuring the whole reaction by driving force.
Right. I mean, evolution never stops. Even if you think that we escape evolution, there is still natural selection of groups, of civilizations, of tribes, or even of species against one another. So there is this kind of pressure. Competition is always there.
Mm-hmm.
This is part of life. And once again, we are competing. I hold myself very strongly not to say what happens with this guy, Homo sapiens, but we are still competing for what? Space, matter, energy, water. So you're correct. There is always, even if you manage to, to liberate yourself as you think from evolution, you're not. You're just making it more brutal or more dangerous. But we are still fighting one another, and we are still competing with one another. And this is part of life.
Mm-hmm. Thank you also for the reaction of the plasma in the early Earth when it comes to the energy, because they are starting the radical reaction. They are super fast to obtain the products.
Who are super fast?
The radical reactions that stimulated by the plasma. In the higher energy reactions, no, they are much more faster to trap the radicals.
That's interesting. Okay. This is where solid data. I mean, this is just a toy model with qualitative formulations. But if it becomes mature enough to put quantitative data in it, that comment about the plasma and the radicals would be very vital. So thank you.
Thank you, Prof.
Okay, Eli Sarid.
Yes, thank you. We don't have many examples to look at, just one basically, the evolution on Earth. And if I look at the history on Earth, I would say that we have roughly 15% of the time that Earth exists for the origin of life, 15% to get from the start of multicellular to what we are today. And then there is the vast 70% that it was just unicellular. So it seems that if you look at the big question of the pace of evolution, especially intelligent species like us, this 70% begs the question. And here I don't see how your arguments would affect much the pace.
Can you continue? So you say we are in a minority. So we became multicellular much later, if I understand your argument. You say that we emerged from unicellular to multicellular fairly late, right? And then how does
So
that?
it took like 500 million, roughly 500 million for years for the origin of life. Then we spent like something like 2 billion years, 2.5 billion years doing nothing much in the unicellular stage. And then all the wonderful things happened in the last 500 million years. So if I ask myself about the rates that would produce an intelligent species, my larger curiosity would be focused on the 2.5 billion years that we were just unicellular on this Earth.
Wait. But let me understand. Once unicellular organism managed to become multicellular, that worked, and they took over, and they emerged immediately, and they formed I mean, if we ever, so here it is, if we ever encounter another biosphere, it's a civilization. So you agree with me, Eli, that they won't be unicellular. They can't. This is not what we may find and with whom we may communicate. Unless you say that as populations they will be intelligent. No, you need something to be multicellular, right? You don't dispute that. You only say that it occurred, we had to wait very long for that, and have we been waiting more and more? I mean, there might be other biospheres which are still not there. But here my question again, suppose that Earth was 10 times larger, much more, thicker hydrosphere and atmosphere, more energy. Wouldn't the emergence of multicellular forms of life would be faster? Now, I think that you're supporting my point. I think you're supporting my point, aren't you?
I'm not arguing against your point, but I felt that you were referring mainly to origin of life and the first stages, and I wanted to focus the discussion on the later stage.
Sure. Okay, I do believe, and I may be once again anthropocentric. I do believe that that was a huge advantage. Just as an engineer, as a mechanical engineer, or just as a simple engineer, you would agree with me that the cooperation of several units, microscopic units, would give a much better efficiency of life rather than the unicellular one. So that has been an advantage. So I can reformulate my question and say, why on Earth? That's nice. Why on Earth? Not on all places. I'm going to put it in the matzaget. Why on Earth did we have to wait so long for the multicellular life to come? The overwhelming majority of our history is unicellular. Why did it take us so long? And then I'll say, you see, you need more space, more matter and more energy, and I'll stick to my claim again. I think so. So I'm thankful for your comment.
Okay. Ricky, did you have a question? Yeah.
A note regarding one series of James Cameron in National Geographic. He showed us there about the life of octopus. So this is a very clever creature and lives only 2 years. And during this year,
Only 2 years? I didn't know that. Octopus?
yeah, and they in order to nurse their children, they leave their places and go to these hot vents in the ocean to nurse them. Otherwise, they cannot flourish.
Thank you. What I think, I mean, Earth is 7/10 being water. Just imagine another planet in which it is on water. So then what we are going to have in spacecrafts are octopi or whatever, or fish or whatever. We are still being very anthropomorphic. But it breaks my heart to know that this amazing creature lives has such a short life. It deserves much more. I have a dog, and I say that he who gave only 15 years to these creatures and wasted on us so many years did a lousy job. So now you're making me even more sad. We are not going to have a discussion without Doron asking questions.
But Doron seems to have gone off the
Doron?
gone off the radar, so I can't find Doron. So
And Illustrator without Doron would
yeah, I know.
not be the same.
So
So if you have more time,
we'll have to save his question for next time, unfortunately. Any more questions?
Only to say,
Yeah.
so nice lecture.
Yeah.
Thank you.
Thank you very much. I grew up, I'm approaching this age in which people reminisce a lot. So I have to write one day about the history of this amazing group. There was a great man. Actually, I have a website. So go to the website. I commemorated my two great teachers, Noam Lahav. It's unfortunately still in Hebrew. I have to translate it. They were great people, Noam Lahav and Shneur Lifson. So I give them tribute in my website. I'll translate it because they were scientists in an international scale. So it's really an honor. I was a very young man when I was introduced to this group, and it's so great to see now a young generation and people continuing the work.
Okay, so if there are no further questions, let's thank our speaker, and thank you, Avshalom, and
Thank you, Nathaniel. Hope to see you
good
soon.
evening, everybody. And
Thank you, Gonen, for this kind invitation. Thank all of you for being here, and I hope that we shall see each other soon in happy circumstances.
okay, and the next meeting is in another month. We'll see you all. Okay, bye-bye.
Thank you. Bye-bye.